We have a question. What's the pH of an aqueous solution of 0.1 molar sodium carbonate? All right, that's a fine question. What are we going to think about it, though? How did we get this salt? It was formed in a neutralization reaction from sodium hydroxide, which is a strong base, and carbonic acid, which is a weak acid. So we are expecting this to be a basic solution. If we don't get a basic solution, we're going to be very unhappy with ourselves. What does carbonic acid do if it's dissolved in water? Well, it forms hydronium ions and then hydrogen carbonate. That's fine. The hydrogen carbonate will then go on and do a second ionization, forming more hydronium and carbonate ions. We expect that when we combine this with the sodium hydroxide, that this first one is going to be entirely consumed and it will all end up going to this hydrogen carbonate. And so this second one of these equilibriums is the one that we're going to use to work with. All right, we have a K value for that. That's good. Since we've decided that's what we're going to work with, this was the information that we needed so that we'd be able to do a rice table with it. We're going to turn it around like this. Carbonate ion and water forming hydroxide ions and hydrogen carbonate, because we're expecting to find a basic solution. So we're going to be looking at it this way, slightly different than this, right? Okay, these each went down by an H+. That's probably the most mystifying part of this, okay? But that's what we're going to work with. What else do I have on this? Oh yeah, a reminder that Ka times Kb is actually the same as Kw. Oh, I didn't want to do that. Now I got to forward through all of that again. Oops, there we go. So we expect all the first ionization to get used up, and we're going to be dealing with this sort of thing. We reorganize it to look like this because we expect this whole thing to end up being a basic solution, and we're trying to find an OH minus. But they gave us a Ka value. This isn't a Ka, it's a Kb, right? I really need a Kb. Well, Kb then is going to be Kw divided by Ka. Now, I might want something to make me believe that is true. If I think about it, Kw, I already had a definition, was the hydronium ion and the hydroxide ion. That was our definition of Kw. For Ka, we will be looking at this one, which would be hydronium ion, and the carbonate. Ooh, 2 minus. Here we go, 2 minus. Over, not this, but this. The hydrogen carbonate ion. If you look at that, you realize these are going to cancel. And since I have two sets of division signs, we're going to end up with HCO3 minus and the OH minus and the carbonate ion down here, which is exactly what we would have gotten from this formula here. So that's sort of, circular. You might find it easier to figure up this first, or you might say, I'm at this, but I know I really want KB, not KA, and when you got done, you would end up with this anyway. Meanwhile, back at the ranch, right? We said that this should always be 1 times 10 to the negative 14. And they gave us this Ka, the 4.7 times 10 to the negative 11. So if I use my calculator on that, I'm going to get that the Kb should be 2.13 times 10 to the negative 4th. Fine. Let us move on now to the actual rice table, now that we have a Kb that will work with this equation. Oh, with that equation. So let's write the equation then. There's the carbonate, and we're combining it with water, which is a liquid and not going to be involved in the actual part that is an equilibrium, forming the hydrogen carbonate ion and hydroxide ion. What do I have initially? Initially, I have 0.1 molar, because when this breaks up, it's going to form 0.1 molar carbonate. So 0.100. On these, oh, well, it's 0. I don't know what they are. Change. This can only go up. When it does, this goes up the same way. Where did they come from? This. So that must have fallen apart. And the equilibrium then is 0.100 minus x, x, and x. This will lead us to saying, if I want to express this as the equilibrium constant Kb, that I'll have x squared, these two, over this 0.100 minus x equals the Kb. And overall, we can massage that into a quadratic equation that looks like this. Equals 0. What does X stand for? Well, in this case, we're going to say it stands for the hydroxide ion concentration. You just find that in the table. So when we solve this for X using the quadratic formula, you know, you're minus B again. This is going to have to be a plus. You're going to take B, whoops, oh man, you can't even read that. 2.13 times 10 to the negative 4th, B squared, minus 4AC, there's a minus, okay, so plus 4 times that. All of that's under your radical, and then over 2. When you get done putting that through your calculator, 0.0045 is what you're going to get for your concentration of OH minus. POH equals negative log of the OH minus. So that's negative log of the 0.0045. Which you're going to get a 2.35. But what did they ask for? They asked for the pH. pH, 14.00 minus the pOH, and you get a pH of 11.65, which is good because that was a strong base and a weak acid, so I expect it to be basic, and it is.